Hey guys, tonight we're going to step into a world that for most of us exists only in the quiet corners of our nightmares. Imagine for a moment that you are not lying in your bed, but rather you are a tiny speck of dust drifting in the air of a world subtly changed. The soft moonlight that filters through your window now casts long, impossibly deep shadows. The gentle creak of your old house isn't the wind, but something else entirely, a subtle vibration echoing through the floorboards. Tonight, we're going to explore a universe where spiders, those small, often overlooked architects of the natural world, have somehow become the size of humans. It's a thought that makes the skin crawl, I know, and let me be perfectly honest with you, in this version of reality, you probably wouldn't survive very long. But that's what makes this thought experiment so fascinating. So rich with questions we can explore from the safety of our blankets. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And as we begin this journey, I'd love to know where you are right now and what time it is for you. Tell me in the comments. We'll be weaving a new story together, a new kind of natural history from all corners of the globe. Let's begin by peeling back the curtain on the silent weaver itself. When we think of a spider, we often picture a tiny eight-legged creature skittering across a corner or suspended in a dew-kissed web. But what if we were to take that tiny blueprint and scale it up not just a little but to the size of a human? What would that magnificent, terrifying creature actually look like? The first thing to consider is its body, a masterpiece of biological engineering. A spider's body isn't a single monolithic structure like ours. It's an exoskeleton, a hard protective armor made of chitin. Imagine that material scaled up to support a weight of, say, 150 pounds. This isn't just about making a bigger bug. It's about a fundamental transformation of its very being. The square-cube law, a beautiful and often brutal principle of physics, tells us that as an object grows in size, its volume increases much faster than its surface area. For our human-sized spider, this means its weight would increase exponentially, while the strength of its chitinous armor, which depends on its cross-sectional area, would struggle to keep up. It would be like trying to build a skyscraper out of matchsticks. The very idea of it standing upright, let alone moving with the speed and agility of its smaller cousins, is a physical paradox. This brings us to the first core scientific concept. We'll explore the square cube law. Think of it this way. Imagine a simple cube with sides of 1 inch. Its surface area is 6 square inches, and its volume is 1 cubic inch. Now double the sides to 2 inches. The surface area is now 24 square inches, 4 times larger, but the volume is 8 cubic inches, 8 times larger. The larger you get, the more this disparity grows. A spider's body is a testament to this law in its original small-scale form. Its lightweight exoskeleton is perfectly suited to its tiny size, providing protection without being so heavy that the spider can't move. But scale that up, and the exoskeleton would need to be impossibly thick and heavy just to bear the creature's own weight. It would be a slow, lumbering beast, perpetually on the verge of collapse. The graceful darting motion we associate with spiders would be a distant memory replaced by a slow, deliberate march. Each step a feat of engineering against the crushing force of its own mass. Now let's turn our gaze to its eyes. Most spiders have 8 eyes, a truly alien arrangement that gives them a near 360-degree view of their world. These aren't the complex lens-based eyes of humans, but a mosaic of simple eyes called ochelli. Each one a small single-lensed unit. In some species like the jumping spider, these eyes are incredibly sophisticated, allowing for precise depth perception and color vision. A jumping spider's vision, a fascinating fact, is in some ways sharper than our own, a tiny marvel of optical science. Imagine those eyes scaled up. The world would not appear as a single coherent image, but as a vast kaleidoscopic tapestry of overlapping pictures. It would see in a way we can barely comprehend, each eye a separate window onto the world, all working in concert. We see the world as a seamless film. Our giant spider would see it as a beautiful, terrifying collage, a silent, flickering movie of its surroundings. The sheer volume of visual data being processed by its nervous system would be staggering, a flood of information so intense it might be more akin to a dream than to waking reality. This visual tapestry leads us to a philosophical question, a quiet mystery that scientists still ponder. What is the nature of sensory experience? Do all creatures perceive reality in the same fundamental way, or is each species' reality a unique construction of its sensory inputs? We see the color red. A bee sees a pattern in a flower petal invisible to us. Our giant spider would see the world as a fragmented, multi-lensed image. Whose reality is the correct one? The truth is, we don't really know for sure. We can only infer from behavior and biology. Perhaps a spider's reality isn't about seeing the world at all, but about feeling it. For a smaller spider, the world is a stage of vibrations, a drum of silent music transmitted through its web. A fly's frantic struggle, a gentle breeze, the footfalls of a predator, all are translated into a language of tremors, a tapestry of touch. Let's talk about that exoskeleton again, but this time from a different angle. It's not just a suit of armor. It's also a part of the spider's growth cycle. Spiders grow by molting, shedding their old, too small exoskeleton to reveal a new, softer one underneath. This is a moment of profound vulnerability for the creature. For our human-sized spider, this process would be a monumental event, a geological shift in its life. Imagine a creature the size of a car trying to shed its skin. It would be an incredibly slow, exhausting process, one that could take days or even weeks. During this time, it would be utterly defenseless, its new skin soft and pliable, leaving it exposed to the elements and to potential predators. The energy required to simply shed its skin and then inflate the new one with hemolymph, the spider's equivalent of blood, would be immense. It would be a metabolic marathon, a feat of biological endurance. The fact that a tiny spider can do this with relative ease is a testament to the elegant efficiency of nature at its smallest scale. The larger you get, the more these simple biological functions become Herculean tasks. The very concept of a spider scaled up to our size forces us to confront our own biological assumptions. We are creatures of bone and muscle, with a closed circulatory system and a central nervous system. Our physiology is designed for our scale. A spider with its external skeleton, its open circulatory system, and its distributed nervous system is designed for its. The idea of a spider with a human-sized brain with the capacity for self-awareness or philosophical thought is pure fantasy. But what if its nervous system, a web of ganglia and nerves distributed throughout its body, were to grow in complexity alongside its size? Would it develop a different kind of intelligence, one not based on a single centralized command center? Like our brain, but on a network of distributed processors, each one responsible for a different limb or function. It's a fascinating question, and one that challenges our very definition of what it means to be intelligent. Maybe intelligence isn't a singular thing, but a vast interconnected network, a web of thought woven throughout the body. The silent weaver's first thread, the one we've just pulled, leads us down a path of interconnected questions. We've touched on physics, biology, and philosophy, all through the lens of a single impossible creature. We've seen how the simple act of scaling up a spider's body reveals profound truths about the laws of nature. We've glimpsed a world of vibrant, kaleidoscopic vision and pondered the very nature of perception. We've considered the staggering challenge of growth and the mystery of consciousness. And this is only the beginning. This first thread is just the start of a much larger web, a story we're just beginning to spin together. The more we pull, the more we will uncover about the delicate balance of our own world and the quiet, elegant horrors of a world that might have been. Having woven the first thread of our tale, we now find ourselves suspended within its intricate structure, gently swaying to the rhythm of our own imagination. we've considered the sheer biological paradox of a human-sized spider, a creature that defies the very laws of scaling that govern life on Earth. But let us now focus on one of its most remarkable and essential features, the very material that defines its existence, its silk. When we see a spider's web, we are looking at a masterpiece of natural engineering, a structure of impossible lightness and unimaginable strength. A spider's silk, in its original small-scale form, is stronger than steel by weight and more elastic than nylon. It is a protein-based fiber that is both incredibly tough and flexible, a marvel that has long fascinated scientists and engineers alike. Now, let's imagine this substance scaled up to match our giant spider. What would that web look like? How would the physics of this material change under the immense strain of supporting not just a large spider, but its massive prey, and even the weight of a world altered by its presence? This brings us to our next core scientific concept, the tensile strength of materials. Tensile strength is simply a measure of how much a material can be stretched or pulled before it breaks. Spider silk, in a technical sense, is not just strong. It's an elegant solution to a complex problem. A spider needs a material that is both strong enough to hold its prey and flexible enough to absorb the shock of impact. Our human-sized spider, however, would need a silk that operates on an entirely different scale of physics. The weight of its own body, as we discussed, would be immense, and the silk would need to bear this load. But let's add to that the weight of the objects it might ensnare: a deer, a car, or even a small building. The silk would need to possess a tensile strength so great that it would likely violate the known principles of molecular bonding and material science. It would have to be something more than just a protein fiber. It would have to be a substance from the pages of science fiction. The energy required to produce such a substance would be equally staggering. A small spider can produce silk from a gland in its abdomen. Our giant spider would likely need a whole new organ, perhaps a series of them, to spin the colossal quantities of silk required. The process would be a metabolic furnace, a continuous, almost ritualistic act of creation. This leads to a little-known but fascinating fact about spider silk. Some species of spiders produce different types of silk for different purposes. There's dragline silk, used for the main framework of the web, and it's the strongest. There's sticky silk, used for catching prey. There's swaddling silk, used to wrap eggs. The list goes on. Our giant spider would have to produce a staggering variety of these, each with unique properties. Its dragline silk would be as thick as a ship's anchor rope, capable of holding immense weight, while its sticky silk would be a super adhesive, a fast-acting polymer, capable of trapping a moving vehicle. Imagine the intricate dance of these different silk types, woven together into a single cohesive structure. The web would not be a delicate shimmering tapestry, but a monumental work of engineering, a forest of thick cables and sticky traps. It would be an architectural masterpiece, a monument to a species that has learned to manipulate the very fabric of physics to its will. But there's a subtle philosophical question lurking here, a question that scientists still struggle with. What is the true nature of biological design? Is the spider's silk simply the result of random mutations and natural selection, a lucky accident of evolution? Or is there something more fundamental, a kind of elegant, preordained intelligence in the very chemistry of life that allows it to create such perfect solutions to its problems? The truth is, we don't really know for sure. We can analyze the molecular structure of silk, we can replicate it in a lab, but we still haven't fully grasped the genius of its natural production. This raises an interesting question. Is the genius in the organism itself, or in the silent cosmic rules that govern its potential? Let's imagine the world transformed by this silk. A human-sized spider's web would not be found in a quiet corner of your room, but stretched between skyscrapers, a vast, shimmering net against the cityscape. It would be a new kind of landscape, a new kind of architecture. The air would be thick with these colossal strands, a silent forest of woven death. For us, it would be an impassable barrier, a tangled web of impossibly strong fibers. For the spider, it would be home. It would be its hunting ground, its nursery, and its sanctuary. It would be a monument to its power, a silent declaration of its dominance over the landscape. The beauty of this thought experiment is that it forces us to reconsider the most mundane things in our world. We take for granted the properties of materials, the stiffness of wood, the ductility of metal, the elasticity of rubber. But what if there were a living creature whose very existence demanded a new understanding of these properties? What if its silk was not just a tool but a fundamental force of nature, a new kind of physics in action? The very air would vibrate with its movements, each plucked strand of silk sending a signal through the web, a silent whisper that reveals the location of its prey. The web would be a vast sensory organ, an extension of the spider's nervous system, a map of its world. We talked about the square cube law in our last segment, and it's a concept that continues to resonate here. The silk our giant spider needs would have to defy this law. Its thickness would have to grow at an even faster rate than its volume, a continuous geometric progression of strength. To support its weight and the weight of its prey, the silk would have to be not just strong, but almost infinitely so. This brings us back to the sheer metabolic cost. A spider silk is made from a liquid protein that is spun into a solid fiber. The energy required to convert a liquid into a solid of such immense tensile strength would be extraordinary. It would be like a small factory running continuously inside the spider's abdomen, a constant churning process of creation. The image of this silent weaver suspended in its colossal web is a powerful one. It speaks to a kind of quiet dominance, a slow methodical takeover of the world. It is not an active chaotic predator like a lion or a wolf. It is a patient architect, a meticulous engineer. It waits for its world to come to it. The web itself is the hunting ground, the trap. The spider is simply the final silent element in a larger, more intricate machine. And the story of this machine is the story of a material so strong, so powerful, that it redefines the very laws of our universe. The weight of its silk, the intricate geometry of its web, the sheer impossible strength of its fiber. All of it is a testament to the fact that sometimes the most dangerous things in the world are not the ones that roar, but the ones that silently build their traps and patiently wait. We've journeyed through the intricate architecture of a human-sized spider's body and marveled at the impossible strength of its colossal silk. Now let us turn our attention inward to the very heart of this immense creature and contemplate the profound challenges that arise from the silent, unforgiving dictates of physics. The transition from a tiny, elegant arachnid to a monumental human-scaled beast is not merely a matter of size. It is a fundamental collision with one of the most beautiful and brutal principles in all of science. The square cube law, which we touched upon before, is not just an interesting tidbit. It is a force that would make the very existence of our giant spider a constant struggle, a silent battle against its own biology. This brings us to our third core scientific concept, which is a deeper exploration of the square cube law and its impact on biology. For a small spider with its tiny body and delicate frame, the square cube law is a benevolent force. Its lightweight and large surface area relative to its volume make it an agile, fast creature. It can scurry up walls, leap great distances, and withstand falls from great heights with no injury, simply because its small mass generates very little momentum. But for our giant spider, this law becomes a crushing weight, a physical burden that would shape every aspect of its life. The spider's internal organs would need to be massively oversized to keep up with the demands of its exponentially larger body mass. Its lungs, if we can even call them that, would need to be a new kind of biological engine. Spiders have what are called book lungs, a series of air pockets with large surface areas, much like the pages of a book that allow for gas exchange. For our colossal arachnid, these book lungs would need to be the size of small rooms, a complex network of tissues constantly working to oxygenate its immense body. But the problem isn't just about the size of the lungs. It's about the very mechanism of breathing. A spider does not have a diaphragm or a rib cage like we do to actively pump air in and out. Instead, air diffuses into its body. For a tiny spider, this process is efficient enough, but for a human-sized spider, diffusion would be impossibly slow. The oxygen would barely penetrate the outer layers of its body, leaving its core suffocated. This raises a fascinating and little-known scientific truth. The limitations of simple diffusion are why insects and arachnids never evolved to be truly massive in our world. It's a natural, invisible ceiling on their growth. To overcome this, our human-sized spider would need a new respiratory system altogether, perhaps a complex network of tracheal tubes with muscular pumps, a biological solution that would have to be invented from scratch by evolution. It would be a breathtaking act of natural engineering, but a necessary one to simply survive. This struggle with gravity and diffusion extends to another critical system: circulation. We humans have a closed circulatory system with a powerful heart pumping blood through a network of arteries and veins. A spider, on the other hand, has an open circulatory system. Its hemolymph, the spider equivalent of blood, simply sloshes around inside its body cavity, bathing its organs in oxygen and nutrients. A single powerful pump would not be sufficient for our giant spider. Imagine trying to pump water through a vast, sprawling sponge. The task would be immense. The pressure required to push the hemolymph to its furthest extremities. The tips of its colossal legs would be extraordinary. Its legs would need a series of one-way valves, a whole new kind of cardiovascular plumbing, to prevent the hemolymph from simply pooling at the lowest points. It would be a hydraulic marvel, a complex system of pumps and channels all working in concert. This leads us to a quiet philosophical question that scientists still grapple with. To what extent does the physical world dictate the possibilities of life? Is evolution a story of limitless potential? Or is it a process of finding the best possible solution within a set of rigid, unbending rules? The truth is, we don't really know for sure. We see the elegant designs of nature and wonder if they are happy accidents or the only possible answers. The fact that life on Earth has not produced insects or arachnids of immense size despite their evolutionary success seems to suggest that the laws of physics are not suggestions, but commands. The square cube law is a silent editor, a meticulous craftsman that has carved out the boundaries of what is possible. Now let's bring our awareness back to our giant spider, a creature that is a living testament to this struggle. Its walk would be a slow, deliberate march, each step a carefully calculated movement against the pull of gravity. Its body would be a constant, silent battleground of competing forces. The immense weight of its mass, the struggle to circulate oxygen and nutrients, the constant need for more energy. It would be a being defined by its own limitations, a walking paradox of immense power and profound fragility. The quiet hum of its existence would be a continuous strain, a constant work just to stay alive. The graceful darting movements of its smaller cousins would be impossible. It would be a slow-motion predator, a patient hunter whose very mass is a weapon. The idea that such a creature could exist even in our imaginations forces us to confront the delicate balance that defines all life. The very air we breathe, the pull of gravity? These are not just abstract concepts. They are the silent architects of our bodies and the ones that would have in our world long ago crushed the very idea of a human-sized spider. The silent battle against gravity and the limitations of diffusion bring us to the very source of a spider's life force, its circulatory system. In our last segment, we touched upon this in passing, a brief whisper of the challenges. Now let's delve deeper into this complex open network and ponder how it would have to be reimagined to sustain a creature of human proportions. Unlike the clean-ordered highways of our own closed circulatory system, where a single powerful heart pumps blood through a network of arteries and veins, a spider system is more like a vast flooded plain. Hemolymph. The spider's life-giving fluid is not contained in vessels, but rather sloshes freely through the body cavity, bathing the organs and tissues in oxygen and nutrients. This elegant low-pressure system works perfectly for a tiny creature that lives a quiet, slow-paced life. But for our giant, its elegance would become its downfall. Its silence, a deafening cry for a new kind of engineering. This leads us to our fourth core scientific concept, the biomechanics of open versus closed circulatory systems. Think of our own circulatory system as a finely tuned irrigation system with a powerful central pump and a network of pipes leading to every single plant in the garden. This system is efficient, high pressure, and allows for the rapid delivery of oxygen and nutrients to every cell in our body. A spider system, in contrast, is more like a beautiful, but much less efficient flood. The heart, a simple tube-like structure, pumps the hemolymph out, but it simply flows through the body cavity before being drawn back in. This works for a small spider because the distances are so short and the demands on its metabolism are relatively low. The oxygen can diffuse directly from the book lungs into the surrounding hemolymph, and from there, it can find its way to the tissues. But imagine this system scaled up. The fluid would struggle to reach the extremities, pooling at the bottom of its body, leaving its colossal legs and head starved of oxygen. The sheer volume of fluid would be immense, and the simple tubular heart would be overwhelmed, a tiny engine trying to power a colossal machine. This is where a fascinating, if little-known fact about spider physiology comes into play. A spider's body has an intricate network of muscles and valves that help to control the flow of hemolymph and, crucially, to extend its legs. Spiders don't have extensor muscles in their legs, the muscles that would allow them to push their legs outward. Instead, they use a form of hydraulic pressure. They pump hemolymph into their legs, which causes them to extend. The retractor muscles, which pull the legs in, are what we think of as muscles. This hydraulic system is a marvel of efficiency for a small spider, allowing for rapid darting movements and powerful jumps. But for our human-sized spider, this system would be impossibly difficult to maintain. The pressure required to move a leg the size of a human's, with the immense weight and momentum that entails, would be extraordinary. The walls of its hydraulic system would have to be impossibly strong to withstand the pressure. It would need a network of auxiliary pumps, a series of smaller hearts, distributed throughout its body, each one working to maintain the pressure in its colossal legs. This raises a quiet philosophical question that scientists still struggle with. What is the true relationship between form and function in biology? Is the spider's unique anatomy simply a result of its size, a perfect adaptation to the rules of its small world? Or is it a testament to the endless creativity of evolution, a story of a creature that has found a completely different but equally valid way to move and to live? The truth is, we don't really know for sure. The fact that spiders have evolved a system so different from our own, a system that works perfectly for their scale, suggests that there is no single right way to build a body. There are only solutions to problems, and the problems are always shaped by the size of the organism. Our giant spider, a creature that breaks all the rules, would have to invent a new kind of biomechanics, a new way to live and move that would be a testament to the sheer force of evolution. The image of this giant spider, a symphony of 8 hearts, each one working in silent concert to pump hemolymph through its colossal frame, is a powerful one. It speaks to a creature that is a walking, breathing paradox. It has an open circulatory system, a simple, elegant design that has been pushed to its absolute breaking point. It is a slow, methodical creature, its every movement a deliberate conscious act against the immense weight of its own body. Its existence is a continuous silent work of hydraulic engineering, a constant pumping and pressurizing, and to simply stand, to simply move. The grace and agility of its smaller cousins are gone, replaced by a slow, powerful, and terrifying presence. Its heart is not a single powerful pump, but a network of many, a distributed intelligence of circulation, a testament to the fact that to survive at this scale, it had to evolve beyond a single solution to become a new kind of being altogether. The silent hum of its many hearts would be a constant presence, a reminder of the immense energy and incredible engineering that would be required to simply keep such a creature alive. With the intricate symphony of its many hearts now a constant hum in our imaginary world, we turn our attention from the inner workings to the most fundamental and demanding of all biological imperatives, the unending need for energy. We've established that our human-sized spider is a creature of immense weight and hydraulic complexity, a walking paradox that requires a new kind of physics to exist. But all of this staggering biological engineering requires fuel. A tiny spider can subsist on a few insects a week, a quiet, almost imperceptible consumption. Our giant, however, would be a metabolic furnace, a continuous engine of hunger that would reshape its entire world. The energy required to simply move, to build its colossal webs, and to maintain its immense body would be so vast that the very landscape would become a hunting ground, a banquet on a scale we can barely comprehend. This brings us to our fifth core scientific concept, metabolism and the ecological pyramid. Metabolism is simply the set of chemical reactions that occur in an organism to maintain life. For us, it's the process of converting food and oxygen into energy. For a spider, it's the same, but with a different set of rules. A small spider, being cold-blooded, has a very slow metabolism. It can sit for days, even weeks, in its web conserving energy and waiting for a meal. But as a creature's size increases, so too does its metabolic rate. A human-sized spider, even if it were cold-blooded, would have such an immense body mass that the sheer number of cells needing energy would be staggering. It would be a perpetual state of hunger, a creature whose very existence is a constant urgent search for its next meal. This leads to a fascinating, though unsettling scientific fact, the concept of the ecological pyramid. At the bottom of this pyramid are producers like plants that create their own food. Above them are the primary consumers or herbivores that eat the plants. Then come the secondary consumers like us who eat the herbivores. And at the very top are the apex predators. Each level of this pyramid requires a massive amount of energy from the level below it. It takes on average 10 pounds of plant matter to produce 1 pound of herbivore and 10 pounds of herbivore to produce 1 pound of secondary consumer. Now imagine our human-sized spider at the very top of this pyramid. It would be an apex predator of such immense size that it would need to consume an unimaginable quantity of prey to sustain itself. A human-sized spider would not be eating a few flies. It would be consuming deer cattle and maybe even larger creatures. The ecological balance of our planet would be completely and utterly shattered. Entire species would be wiped out simply to fuel the unending hunger of these magnificent, terrifying creatures. This raises a quiet philosophical question that scientists still grapple with. What is the true cost of existence in the natural world? We look at a cheetah running at top speed and see a beautiful act of nature. But is it not also a violent act, a desperate measure to simply survive? Our human-sized spider, in its constant unending search for food, is a symbol of this brutal truth. Its hunger is not a choice. It is a necessity. Its violence is not born of malice. It is born of a profound biological imperative to simply live for another day. The truth is, we don't really know for sure what the morality of the natural world is. We only see the mechanics of survival, the constant churning cycle of life and death, consumption and creation. Let's imagine what this unending hunger would look like. A human-sized spider would not be a quiet, silent hunter. Its movements would be slow, deliberate, but its presence would be a constant looming threat. Its web would be not just a trap, but a sign, a declaration of a territory where all other life is simply food. The silent forests and fields would become a vast pantry, a larder for a creature that never stops eating. Its metabolism would be a fire that never goes out, a continuous burning that demands more and more fuel. It would be a creature of consumption, a being whose entire existence is defined by the unending quiet echo of its own hunger. It would be a living monument to the brutal and beautiful efficiency of nature, a creature that has pushed the boundaries of life, and in doing so, has become a symbol of both the elegance and the terrifying violence of the world. Its sheer unimaginable need for sustenance would make it a force of nature, a living, breathing testament to the fact that in the quiet corners of our universe, some creatures exist only to eat, to grow, and to consume. The unending hunger, the constant fire of metabolism, leads us down a darker, more philosophical path. We have considered the physical, the biological, the material. But what about the inner life of this colossal creature? Does a spider, a being so alien to us in its form and function, possess anything we might recognize as consciousness? Does it have thoughts, feelings, a sense of self? Or is it a perfect biological machine, a silent automaton of instinct and physics? The question of consciousness is a mystery that has haunted philosophers and scientists for centuries, and our human-sized spider offers a new and perhaps unsettling lens through which to view it. This brings us to our sixth core scientific concept, the nature of consciousness and the difference between instinct and intelligence. We tend to view consciousness as a purely human trait, an emergent property of our large complex brains. We have self-awareness, the ability to reflect on our own existence, to imagine the future, and to remember the past. Our human-sized spider, however, would have a nervous system that is fundamentally different. It is not a single centralized brain, but a distributed network of ganglia or nerve clusters that are spread throughout its body. It's a decentralized command center, a web of interconnected processors, rather than a single powerful computer. How would such a system give rise to consciousness? Would it even be possible? This is where a fascinating, if little-known scientific fact comes into play. Even tiny spiders, like jumping spiders, exhibit what we might call complex behaviors. They hunt with a strategy, plotting a path to their prey. They can learn from their mistakes and adjust their hunting tactics. They can even solve simple puzzles to get a food reward. These behaviors suggest a level of intelligence, a form of complex problem-solving. But is this intelligence the same as consciousness? Is it the same as the self-awareness that allows us to look at ourselves in a mirror and recognize our own reflection? The truth is, we don't really know for sure. It's a difficult question to answer because we can't simply ask a spider what it's thinking. We can only observe its behavior and infer its inner life. This raises a quiet philosophical question that scientists still grapple with. What is the line between a complex biological machine and a truly conscious being? Is consciousness simply the result of a certain level of complexity in a nervous system? Or is there something else, some other ingredient, that we have yet to discover? The idea of our human-sized spider with its decentralized nervous system and its complex instinctual behaviors forces us to confront this question head-on. Is it a silent, thoughtless automaton, a perfect predator that simply follows the dictates of its genes? Or is it a being with a new kind of mind, a consciousness that is distributed throughout its body, a vast interconnected network of awareness that we can barely begin to imagine? Let us imagine what this mind might be like. It would not be a mind of words or of images, but a mind of vibrations, of touch of silk. Its thoughts would not be linear, but a vast, silent hum of sensory data, a constant stream of information from its 8 eyes, its hairs, and its web. Its memories would not be of stories or of faces, but of the feel of a particular prey, the tension of a particular thread, the subtle changes in the air currents. It would be a mind of pure sensation, a consciousness that is not separate from its body, but is its body. It would be a being that is so fundamentally different from us that its inner life might be more alien than anything we could ever imagine. The quiet hum of its existence would be a continuous stream of sensory data, a constant silent work of processing and reacting. It would be a living monument to the fact that consciousness may not be a single monolithic thing, but a vast, shimmering spectrum of experiences, a new kind of mind that has emerged from the very fabric of life itself. And the more we contemplate it, the more we realize that the greatest mystery of this human-sized spider isn't its size or its strength, but the silent, uncharted territory of its mind. Having peered into the silent, distributed consciousness of our colossal spider, we must now rewind the clock. Before there was a mind, before there was a body, there was simply time. The story of our giant arachnid is not just a thought experiment about a single creature, but a grand sweeping narrative that must have unfolded over eons. How could such a magnificent, terrifying being have come to be? To answer that, we must venture into the deep past, to the primordial soup and the ancient forests where the very first threads of life were spun. The existence of our human-sized spider in this hypothetical universe is an evolutionary tale, a whisper from the ancient weave of time that speaks of a different path for life on Earth. This brings us to our seventh core scientific concept: evolution and the deep time lineage of arachnids. We know that spiders in our world have been around for an incredibly long time. The oldest known spider fossil dates back to the Devonian period over 300 million years ago. These ancient spiders were much smaller than the ones we know today, but their basic body plan, the 8 legs, the fangs, the silk-producing glands, was already in place. Now let's imagine a different history, a subtle deviation in the grand tapestry of evolution. What if at some point, a branch of the arachnid family tree was not constrained by the square-cube law? What if in a world with higher oxygen levels or a different gravitational pull, a species of spider began to grow slowly but inexorably from a tiny, elegant hunter into a colossal dominant force? This is where a fascinating, if little-known fact about evolution comes into play: mass extinction events. Our planet has experienced several of these periods of time where a large percentage of all life on Earth simply vanished. The most famous is the one that wiped out the dinosaurs. These events are often seen as catastrophes, but for some species, they are a moment of opportunity. The sudden disappearance of dominant predators and competitors creates a vacuum, a blank slate for life to fill. What if during one of these extinction events, a species of spider that had already begun to grow in size suddenly found itself without competition? What if it was able to fill the niche of apex predator, a role that in our world was filled by dinosaurs and later by mammals? It's a tantalizing thought, a single twist in the long-flowing river of time that could lead to an entirely different world. This raises a quiet philosophical question that scientists still grapple with. Is evolution a linear path toward greater complexity and perfection? Or is it a sprawling, chaotic bush, a story of chance and circumstance? The truth is, we don't really know for sure. The fact that a creature like a human-sized spider seems so impossible in our world suggests that our universe has a set of rules, a set of physical laws that have been the ultimate architects of life. But what if those rules were different, just a little? What if a different planet, a different timeline, a different set of circumstances allowed for a different kind of life? Our human-sized spider is a beautiful symbol of this, a creature that is both familiar and alien, a ghost from an evolutionary past that might have been. The story of our giant spider, then, is a story of survival against all odds, a tale of a creature that navigated the great extinction events of Earth's past, a silent witness to the rise and fall of empires of life. It would have been a quiet, patient creature, a master of adaptation, a being whose existence was a continuous methodical act of survival. It would have outlived the dinosaurs. It would have watched the first mammals scurry in the shadows, and it would have, through sheer evolutionary will, carved out a new place for itself at the very top of the food chain. Its lineage would be a long, unbroken thread, a tapestry of time woven with the quiet hum of its many hearts and the impossible strength of its colossal silk. The story of its past is not a violent, chaotic one, but a slow, patient, and methodical march toward a future that for us is an unsettling present. And the more we contemplate its history, the more we realize that the greatest mystery of this human-sized spider isn't its size or its strength, but the silent, uncharted territory of its evolutionary journey. As we listen to the faint echoes of our giant spider's ancient past, we now turn our attention to its present, to the way it would experience and interact with the world around it. We as humans are creatures of sight and sound. We communicate with words, with tone, with the subtle expressions of our faces. But a spider's world is a silent one, a symphony of vibrations and touch. It is a world where communication is not a matter of a raised voice, but a plucked thread. It is a language as old as life itself, and for our colossal arachnid, it would be a language on a monumental scale. This brings us to our 8th core scientific concept, the language of vibration and silk. Spiders do not have ears like ours. They don't hear the world in a linear sequential way. Instead, their world is a vast interconnected network of sensory information that they perceive through the tiny hairs that cover their bodies and the intricate web they build. These hairs, called trichobothria, are so sensitive that they can detect the tiniest air currents, the faintest vibrations. For a small spider, this allows it to pinpoint the location of its prey or a potential mate with incredible precision. Its web is not just a trap. It is a giant ear, a sensitive sensory organ that translates the world into a language the spider can understand. Now imagine the system scaled up to human size. The language of vibration would become a new kind of sensory landscape, a silent, powerful force that would reshape its entire world. The colossal strands of its web would act as a vast interconnected communication network. A single vibration, a single plucked thread would travel through the web at the speed of sound, a silent whisper that could be felt for miles. A prey's frantic struggle, the rumble of an earthquake, the footfalls of a passing human. All of these would be translated into a language of tremors, a tapestry of touch that the spider could understand. The spider would not just see its world, it would feel it. Its entire existence would be a continuous, silent hum of sensory data. This leads to a fascinating, if little-known scientific fact. Some spiders, like certain species of tarantulas, can produce vibrations themselves. They can stridulate or rub two body parts together to produce a sound that we would hear as a hiss. For our giant spider, this could be a new form of communication. A low, powerful rumble, a deep hum that would travel through the ground and up through the roots of trees, a silent declaration of its presence. It would be a language without words, a conversation of pure, unadulterated vibration. It would be a new kind of dialogue, a powerful and ancient form of communication that would reshape our understanding of what it means to speak and to listen. This raises a quiet philosophical question that scientists still grapple with. Is the richness of a creature's inner life tied to the complexity of its language? We, as humans, believe that our ability to use complex language is what makes us truly conscious, truly intelligent. But what if there is another way? What if a language of vibration and silk, of pure sensation and touch, is just as rich, just as complex? The truth is, we don't really know for sure. The idea of our human-sized spider, a creature that communicates with the very fabric of its world, forces us to confront this question head-on. Is it a silent automaton, a being that simply reacts to its world? Or is it a being with a new kind of mind, a consciousness that is not tied to words, but to the constant silent hum of its existence? The image of this silent weaver suspended in its colossal web is a powerful one. It speaks to a kind of quiet dominance, a slow, methodical takeover of the world. It is not an active, chaotic predator like a lion or a wolf. It is a patient architect, a meticulous engineer. It waits for its world to come to it. The web itself is the hunting ground, the trap. The spider is simply the final silent element in a larger, more intricate machine. And the story of this machine is the story of a language so rich, so powerful, that it redefines the very laws of our universe. The weight of its silk, the intricate geometry of its web, the sheer impossible strength of its fiber. All of it is a testament to the fact that sometimes the most dangerous things in the world are not the ones that roar, but the ones that silently build their traps and patiently wait. We have felt the silent vibrations of our giant spider's world, a world where the language of silk and tremor has replaced the noise and clamor we take for granted. Now let's shift our perspective to the world itself, the one reshaped by this magnificent, terrifying creature. If a human-sized spider were to exist, it would not be a passive resident. It would be a master architect, an engineer of silent cities, and its colossal webs would be more than just traps. They would be a new kind of landscape, a new kind of architecture that would transform our forests and our skylines. This brings us to our 9th core scientific concept, biological architecture and the principles of structural engineering. For us, architecture is the art and science of designing and constructing buildings. We use steel, concrete, and glass. We calculate stress strain and load-bearing capacity. A small spider does the same, but with an elegance and an efficiency that we can only marvel at. Its web is a perfect example of a structure that uses the least amount of material to achieve the greatest strength. It is a masterpiece of geometry and tension, a self-correcting system that can absorb the impact of a struggling insect without tearing itself apart. The tensile strength of its silk, as we discussed earlier, is a key component of this. Now let's imagine this scaled up. A human-sized spider's web would not be a delicate shimmering tapestry. It would be a monumental work of engineering, a forest of thick cables and sticky traps. The main drag lines, which would need to be as thick as a ship's anchor rope to support the spider's immense weight, would be woven between skyscrapers and mountain peaks. The air would be a constant humming web of impossibly strong fibers, an impenetrable barrier to all but the most powerful forces. Our cities, our forests, our very landscapes would be transformed into new, beautiful, and terrifying architectural landscapes. The spider's home would be our new reality. This leads to a fascinating, though little-known scientific fact about spider architecture. They don't just build webs, they also build shelters. Some species of spiders build elaborate burrows or nests out of silken leaves. They are master excavators and builders, creating entire habitats for themselves. Our giant spider, in addition to its colossal webs, would likely be a master of burrowing and construction. It might build vast underground layers, a network of tunnels and chambers woven with its impossibly strong silk. These layers would be its sanctuary, its nursery, and its command center, a silent fortress from which it could monitor its vast humming web. It would be an entirely new kind of creature, one that is not just a hunter, but also a builder, a silent architect of its own world. This raises a quiet philosophical question that scientists still grapple with. Is there a fundamental universal principle of design that governs both nature and human invention? We look at the elegant geometry of a spider's web and the elegant geometry of a suspension bridge, and we see a shared principle of efficiency and strength. Is this a coincidence, or is it a testament to the fact that the laws of physics are the ultimate architects, and that all life and all human invention is simply a response to those laws? The truth is, we don't really know for sure. The idea of our human-sized spider, a creature that is both a part of nature and a master of engineering, forces us to confront this question head-on. Is it a silent automaton, a being that simply follows the dictates of its genes? Or is it a master of design, a being that has learned to manipulate the very fabric of physics to its will? The image of a silent city crisscrossed with colossal strands of silk is a powerful one. It speaks to a kind of quiet dominance, a slow, methodical takeover of the world. It is not an active, chaotic predator like a lion or a wolf. It is a patient architect, a meticulous engineer. It waits for its world to come to it. The web itself is the hunting ground, the trap. The spider is simply the final silent element in a larger, more intricate machine. And the story of this machine is the story of a material so strong, so powerful, that it redefines the very laws of our universe. The weight of its silk, the intricate geometry of its web, the sheer impossible strength of its fiber, all of it is a testament to the fact that sometimes the most dangerous things in the world are not the ones that roar, but the ones that silently build their traps and patiently wait. The silent cities of silk, the colossal webs humming with the language of vibration, have become the backdrop of our imagination. But within this new landscape, a new, more profound drama must unfold: the struggle for survival. We have a human-sized spider, a creature of immense power and unending hunger. And we have the world, a world of life that must now contend with a new apex predator. This is not just a story of a single creature. It is a story of a completely and utterly shattered ecosystem, a world where the predator-prey dynamics have been turned on their head. This brings us to our 10th core scientific concept, the ecological balance, and the concept of an apex predator. In our world, an ecosystem is a delicate, intricate web of life where every creature from the tiniest microbe to the mightiest whale has a role to play. The food chain, or more accurately, the food web, is a complex system of producers and consumers, a constant, churning cycle of life and death. At the top of this web are the apex predators, creatures like wolves, lions, or killer whales. They are at the top of their game with no natural predators of their own. They play a crucial role in maintaining the health of the ecosystem by controlling the populations of the animals below them. Now imagine our human-sized spider in this role. It would not be an apex predator in a traditional sense. It would be a cataclysmic force, a being so far removed from the rest of the ecosystem that it would completely and utterly dominate it. A single human-sized spider would have the ability to hunt and kill creatures that in our world are at the top of their own food chains. A deer, a wolf, a bear, all would be simply food, a source of energy to fuel the spider's unending hunger. The silent forests and fields would become a vast pantry, a larder for a creature that never stops eating. Its presence alone would reshape the behavior of every other creature in its territory. Herbivores would be in a constant state of fear, a continuous search for a safe place to feed. Smaller predators would be driven to extinction, their prey either consumed by the giant spider or simply too scarce to sustain them. The entire ecological balance of the planet would be completely and utterly shattered. This leads to a fascinating, though little-known scientific fact about ecosystems: the concept of a keystone species. A keystone species is a species that has a disproportionately large effect on its natural environment relative to its abundance. An ecosystem would be dramatically different or cease to exist altogether if a keystone species were removed. Our human-sized spider would be the ultimate keystone species, a creature whose very existence would shape the entire world around it. Its removal would not just be a loss, it would be a complete and utter collapse of the new terrifying ecosystem it had created. It would be a living monument to the fact that sometimes the most powerful creatures are not the ones that roar, but the ones that silently build their traps and patiently wait. This raises a quiet philosophical question that scientists still grapple with. What is the true nature of balance in the natural world? Is a balanced ecosystem a peaceful, harmonious one? Or is it a constant churning cycle of life and death, consumption and creation, where every creature is simply playing its part in a larger, more brutal, and more beautiful story? The truth is, we don't really know for sure. The idea of our human-sized spider, a creature that is a living testament to the brutal efficiency of nature, forces us to confront this question head-on. Is it a monster? Or is it simply a creature that has found its place, however terrifying, in a world that has allowed it to exist? The quiet hum of its existence would be a constant presence, a reminder of the immense power and incredible engineering that would be required to simply keep such a creature alive. The silent dance of giants, the delicate balance of our ecosystem, shattered and remade by the presence of a new apex predator, brings us to the most fundamental challenge of all movement itself. We've talked about the sheer weight of our human-sized spider, the hydraulic pressure it would need to simply stand. But let's delve deeper into this, to the very physics of locomotion and the profound paradox of its 8 legs. The elegant darting movements of a small spider are a marvel of biological engineering. For our giant, however, this elegance would be a distant memory, replaced by a slow, deliberate march against the immense strain of its own existence. This brings us to our 11th core scientific concept, the paradox of hydraulic locomotion and the biomechanics of movement. We as humans move through a system of bones, muscles, and joints. We have extensor muscles that allow us to straighten our limbs and flexor muscles that allow us to bend them. A spider system, as we touched on before, is much different. It uses a hydraulic system, pumping hemolymph into its legs to extend them. Its muscles, the retractor muscles, are only used to pull them in. It's an incredibly efficient system for a small creature, allowing for rapid jerky movements and powerful leaps. But as a creature gets bigger, this system would become an engineering nightmare. Imagine a simple hydraulic lift. The pressure required to lift a car is immense. Now imagine a hydraulic system that not only has to lift a car, but also has to move it with some semblance of grace and speed. The pressure required would be extraordinary. The walls of the hydraulic system would need to be impossibly strong to withstand the pressure, and the energy required to pump the hemolymph would be staggering. Our human-sized spider would not be able to leap or scurry. Its every movement would be a slow, deliberate act of will against the crushing force of its own weight. Its walk would be a constant, silent battle against gravity, a continuous work of hydraulic engineering, just to take a step. This leads to a fascinating, if little-known scientific fact about spider anatomy. The legs of some spiders, like the tarantula, have a kind of passive hydraulic system. They can lock their legs into a straight position with a very small amount of muscle power. This allows them to stand for long periods of time without expending a lot of energy. For our human-sized spider, this passive system would be a necessity. It would be a creature that, more often than not, would be in a state of quiet stillness, a patient hunter that conserves its energy for the final sudden moment of the kill. Its movements would be rare, but when they came, they would be a cataclysmic force, a slow, methodical march of an 8-legged giant. This raises a quiet philosophical question that scientists still grapple with. What is the true nature of power in the natural world? Is power a matter of speed and agility, like a cheetah? Or is it a matter of sheer, unadulterated mass and strength, like our human-sized spider? The truth is, we don't really know for sure. The idea of our human-sized spider, a creature that is a living testament to the power of pure mass, forces us to confront this question head-on. Is it a monster? Or is it simply a creature that has found its place, however terrifying, in a world that has allowed it to exist? The quiet hum of its existence would be a constant presence, a reminder of the immense power and incredible engineering that would be required to simply keep such a creature alive. The image of this slow, deliberate giant, its every step a testament to the brutal efficiency of nature, is a powerful one. It speaks to a kind of quiet dominance, a slow, methodical takeover of the world. It is not an active, chaotic predator like a lion or a wolf. It is a patient architect, a meticulous engineer. It waits for its world to come to it. The web itself is the hunting ground, the trap. The spider is simply the final silent element in a larger, more intricate machine. And the story of this machine is the story of a creature whose very existence is a testament to the fact that sometimes the most dangerous things in the world are not the ones that roar, but the ones that silently build their traps and patiently wait. Our journey into the world of the human-sized spider has been one of science, of philosophy, of biology, and physics. But now, let's turn our gaze inward from the spider to ourselves and confront the most profound and visceral reaction to this impossible creature fear. For many of us, the sight of a small spider is enough to trigger a sense of unease, a primal ancient fear that we can't quite explain. But what if that small fleeting fear were to become a real tangible threat? What if the creature from our quiet nightmares were to walk among us, a living, breathing testament to our deepest anxieties? This brings us to our 12th core scientific concept, the psychology of phobias, specifically arachnophobia. A phobia is an irrational, persistent fear of an object or a situation. Arachnophobia, the fear of spiders, is one of the most common phobias in the world. It's a fear that seems to be hardwired into our brains, a deep-seated anxiety that we can't quite shake. The question is, why? Why do we fear spiders so much more than, say, bees or wasps, which are far more likely to sting us? There are a few theories. One is that our fear of spiders is an evolutionary leftover, a primal instinct that helped our ancestors survive in a world where venomous spiders were a real threat. We see a spider, and our brain in a split second registers it as a potential danger. Another theory is that our fear is a learned behavior, something we pick up from our parents, our friends, or our culture. We see a spider and we learn to associate it with fear and disgust. Now imagine this deeply ingrained, often irrational fear, confronted with a creature that is in every way a rational reason to be afraid. Our human-sized spider is not just a small creepy crawly. It is a creature of immense power and strength, a being that could easily overpower and kill a human. The fear would no longer be a phobia. It would be a rational response to a real and present danger. The silent cities of silk, the colossal webs humming with the language of vibration, would no longer be a subject of fascination. They would be a sign of a new terrifying reality. The fear would not be a quiet unease. It would be a constant gnawing anxiety, a low hum of terror that would permeate every aspect of our lives. This leads to a fascinating, though little-known scientific fact about fear: the amygdala. A small almond-shaped part of our brain is the center of our emotional responses, including fear. When we see a spider, the amygdala is activated, triggering a cascade of physiological responses. Our heart rate increases, our palms sweat, our breath quickens. This is our fight or flight response, an ancient automatic system that prepares us for danger. In our world, where the threat is a small spider, this response is often an overreaction. But in a world with a human-sized spider, this response would be a perfectly calibrated, necessary function. Our brains, which have been trained for eons to fear a small, harmless creature, would suddenly find themselves in a world where that fear is not just justified, but essential for survival. This raises a quiet philosophical question that scientists still grapple with. Is fear a tool of survival, or is it a barrier to understanding? We look at our arachnophobia and see a deeply ingrained, often irrational fear. But what if that fear is a necessary part of our biological toolkit, a whisper from our ancestors that has helped us survive for millennia? The truth is, we don't really know for sure. The idea of our human-sized spider, a creature that is a living testament to the power of our fear, forces us to confront this question head-on. Is it a monster? Or is it simply a creature that has found its place, however terrifying, in a world that has allowed it to exist? The quiet hum of its existence would be a constant presence, a reminder of the immense power and incredible engineering that would be required to simply keep such a creature alive. Having confronted the chilling reality of our own primal fear, let us now step back and view this world from a more poetic, more philosophical vantage point. The human-sized spider, with its colossal silk and silent humming existence, is not just a monster. It is a living, breathing metaphor for the interconnectedness of all life, a silent weaver of a vast, unseen tapestry that binds all things together. Its silk, impossibly strong and meticulously spun, is a physical representation of the delicate balance that defines our planet's biosphere, a balance that could be shattered by the arrival of a single new force. This brings us to our 13th core scientific concept, the biosphere as a unified system. The biosphere is the part of the Earth and its atmosphere in which living organisms exist. It's a vast, intricate network of ecosystems, all interconnected, where the health of one part depends on the health of all the others. The water cycle, the carbon cycle, the flow of energy from the sun to the plants to the animals, all of these are a part of this great unified system. We, as humans, tend to view ourselves as separate from this system, as observers or as masters. But in reality, we are just one part of it, a single thread in a vast interconnected web. Our human-sized spider with its colossal webs is a beautiful and terrifying symbol of this interconnectedness. Its webs would not just be a new form of architecture, they would be a new kind of nervous system for the planet. The vibrations from a single plucked thread would travel for miles, a silent whisper that could be felt by all. The spider's hunger, its endless need for food, would not just affect its own prey. It would send ripples of change throughout the entire ecosystem. From the plants at the bottom of the food chain to the predators at the top, its very existence would be a continuous silent work of reshaping the world, a living testament to the fact that no living thing exists in isolation. This leads to a fascinating, if little-known scientific fact about the biosphere, the concept of trophic cascade. A trophic cascade is an ecological process that starts at the top of the food chain and tumbles all the way down to the bottom. For example, if you reintroduce wolves to a national park, they start to prey on the deer. The deer in turn become more cautious and eat less in one place. This allows the plants to grow back, which in turn provides new habitats for birds and small animals. Our human-sized spider would be the ultimate trophic cascade, a creature whose very existence would send ripples of change throughout the entire ecosystem. Its arrival would not just be a new predator, it would be a new kind of natural law, a new kind of physics that would reshape the very fabric of life. This raises a quiet philosophical question that scientists still grapple with. Is the biosphere a system of competing individuals? Or is it a single unified organism, a living, breathing planet? We look at our own lives and see a story of individual struggle and triumph. But what if we are all just a part of a larger whole, a single cell in a vast interconnected body? The truth is, we don't really know for sure. The idea of our human-sized spider, a creature that is a living testament to the power of interconnectedness, forces us to confront this question head-on. Is it a monster? Or is it simply a new kind of natural law, a new kind of physics that has emerged from the very fabric of life itself? The quiet hum of its existence would be a constant presence, a reminder of the immense power and incredible engineering that would be required to simply keep such a creature alive. We have felt the fear, and we have contemplated the fragile, interconnected web of life. Now let us bring our awareness to a single culminating moment, a final encounter in this world of silent giants. The story of a human-sized spider is not just a grand sweeping narrative of science and philosophy. It is also a story of personal visceral experience. What would it feel like to stand face to face with such a being? To not just know it exists, but to feel its presence, to witness its power, to become a part of its terrifying reality. This brings us to our 14th core scientific concept, the phenomenology of perception and the sensory weight of an experience. Phenomenology is a branch of philosophy that deals with the study of consciousness and the structures of experience. It's about how things appear to us, how we perceive the world with our senses, and how those perceptions shape our reality. We tend to think of our senses as a window to the world, a passive way of receiving information. But in reality, our perception is an active, creative process, a continuous, subjective interpretation of the world around us. A loud noise isn't just a sound. It's a sudden, jarring change in our reality. A beautiful sunset isn't just a collection of colors. It's an emotion, a feeling of peace and awe. Now imagine this sensory experience applied to our human-sized spider. The encounter would not just be a visual one. It would be a full-body experience, a sensory overload that would challenge the very limits of our perception. The air would be thick with the hum of its existence, a low, powerful vibration that would resonate in our bones. The ground would shake with its slow, deliberate footsteps, each one a testament to its immense weight and power. The smell would be a new kind of natural scent, a blend of silk and prey, and the quiet hum of its own biology. The sight would be a terrifying and beautiful masterpiece of nature, a creature of such immense proportions that it would fill our entire field of vision. The sheer scale of it, the impossible grace of its many legs, the alien geometry of its 8 eyes, all of it would be a profound, life-altering experience. This leads to a fascinating, if little-known scientific fact about our own perception, the concept of the uncanny valley. The uncanny valley is a hypothesis in aesthetics that suggests that human replicas that are very realistic, but not perfectly so, will elicit a sense of unease or revulsion in the observer. It's the feeling we get when we look at a highly realistic robot or a CGI character that is almost, but not quite human. Our human-sized spider is not a replica of a human, but it is a creature that defies our expectations, a being that is both familiar and alien. It is a spider, a creature we have seen 1,000 times, but it is also something else entirely, a being of such immense scale and power that it crosses a kind of uncanny valley of nature. It is a beautiful, terrifying paradox, a living testament to the fact that sometimes the most frightening things are not the ones that are completely unknown, but the ones that are almost, but not quite, what we expect them to be. This raises a quiet philosophical question that scientists still grapple with. Is reality a single objective truth, or is it a subjective personal construction of our own minds? We look at a spider and see a small, elegant hunter. But our human-sized spider forces us to confront the fact that our perception is not a passive reception of data, but an active, creative process. The truth is, we don't really know for sure. The idea of our human-sized spider, a creature that is a living testament to the power of our perception, forces us to confront this question head-on. Is it a monster? Or is it simply a new kind of natural law, a new kind of physics that has emerged from the very fabric of life itself? The quiet hum of its existence would be a constant presence, a reminder of the immense power and incredible engineering that would be required to simply keep such a creature alive. We have confronted the fear, and we have contemplated the fragile interconnected web of life. We've even imagined a final visceral encounter. Now, as our journey comes to a close, we must turn our attention to the one thing that remains after all else is gone: legacy. The story of our human-sized spider is not just a thought experiment about a single creature. It is a grand, sweeping narrative about the rise and fall of species, a tale of what remains and what is lost in the silent grinding gears of time. This brings us to our 15th and final core scientific concept: the geological and cultural record of a species. In our world, the history of life is written in the rocks and the fossils and the artifacts that we dig from the ground. A fossilized bone, a petrified tree, a piece of pottery. All of these are a part of the record, a silent whisper from the past that tells us a story of what came before. The geological record is a story of eons of continents drifting and mountains rising and falling. The cultural record is a story of minds and ideas of art and language and memory. Together they form a tapestry of time, a rich and complex narrative of our planet's past. Now imagine our human-sized spider, a creature that has reshaped the very landscape of our world. What traces would it leave behind? The geological record would be a story of colossal webs of petrified silk as thick as an anchor rope, a silent testament to a creature that once dominated the planet. The fossilized remains of its prey, from deer to elephants, would be found in the tangled remains of its webs, a kind of natural morgue that tells a story of a new kind of food chain. Its own fossils would be a testament to a new kind of biology, a creature of such immense size and power that it would be a geological event in itself. The slow, deliberate march of its 8 legs would leave tracks in the soft earth tracks that would over time become a part of the permanent record, a silent declaration of its existence. The cultural record, however, would be a different story. It would be a story of fear and awe of a creature that has entered our collective consciousness and has become a part of our mythology. Our art, our stories, our myths would be filled with the image of a colossal spider, a silent weaver that controls our world. Our phobia, which in our world is a quiet, irrational fear, would become a new kind of religion, a new kind of wisdom that is passed down from generation to generation. The image of the spider would no longer be a source of unease. It would be a source of reverence, a symbol of a power so immense that it is both beautiful and terrifying. This leads to a fascinating, if little-known scientific fact about memory, the concept of cultural memory. Cultural memory is a way that a group of people, a society or a culture, remembers its past. It's not just about facts and figures. It's about stories and myths and rituals. Our cultural memory of the human-sized spider would not be a historical record of dates and events. It would be a living, breathing part of our culture, a story that is told around the fire, a myth that is whispered to children at night. It would be a part of our collective identity, a constant reminder of a time when the world was ruled by silent giants. This raises a quiet philosophical question that scientists still grapple with. What is the true legacy of a species? Is it the fossils and artifacts it leaves behind? Or is it the stories and myths it inspires, the way it changes the very fabric of our culture and our minds? The truth is, we don't really know for sure. The idea of our human-sized spider, a creature that is a living testament to the power of memory, forces us to confront this question head-on. Is it a monster? Or is it simply a creature that has found its place, however terrifying, in a world that has allowed it to exist? The quiet hum of its existence would be a constant presence, a reminder of the immense power and incredible engineering that would be required to simply keep such a creature alive. And so we have come to the end of our journey. We have pulled on the threads of a single impossible idea and have watched as an entire world, a new kind of natural history, was woven before our eyes. We started with the quiet, elegant horrors of a human-sized spider and ended with a profound philosophical question about the nature of our own existence. We have explored the silent battles of physics, the mysteries of consciousness, and the deep, rich tapestry of time. We have felt the fear, and we have felt the awe. I'd like to gently ask you one last time, where is the place you're staying now? The time in that place at this very moment. How is it flowing? I'd like you to slowly bring your awareness back to the quiet of your own room, to the gentle pull of gravity on your own body. Feel the soft fabric of your sheets, the cool air on your skin. The world of silent giants and colossal webs is now a part of your own mind, a story that you have helped to tell. It is a part of the quiet, beautiful tapestry of your own imagination. Now, as you drift toward sleep, know that the universe is a vast, interconnected place, full of mysteries and wonders that we can only begin to imagine. Let your mind wander into those quiet corners, those unlit rooms, and find peace in the knowledge that even in the most impossible of places, there is a story to be told. Sleep well, my companion, wherever and whenever you are. Sweet dreams.